Today, our modern, highly interconnected world operates in a state of absolute dependence on a single chemical formula. Lithium-ion conquered the market because it was highly adaptable. It originated as the power source for 1990s electronics, like pagers and flip phones, and eventually scaled up to run modern electric vehicles. Its core triumph was simple. It packed high amounts of energy into a tiny physical footprint, and it was rechargeable. It immediately solved the urgent consumer need for portable power. But taking the exact same chemistry that runs a pocket-sized smartphone and scaling it up to stabilize a national power grid stretches the technology well past its natural physical boundaries. The first boundary is physical. Traditional lithium-ion relies on a liquid electrolyte to move charges. Under heavy stress or physical damage, this liquid can overheat and ignite in a chain reaction known as thermal runaway. This map shows the global production share of key battery materials, exposing a secondary vulnerability: supply chain bottlenecks. Looking specifically at cobalt and nickel, production is heavily concentrated in just a handful of countries. This choke point exposes manufacturers to massive geopolitical risks. We have pushed a single chemical formula to its absolute limits in both structural safety and global supply. The era of relying on one universal battery is over. Engineers are no longer searching for a single replacement. Instead, they are developing specialized contenders, with each new chemistry designed to correct a specific flaw in lithium-ion. Solid-state technology approaches the fire risk by entirely removing the flammable liquid electrolyte, replacing it with a solid, stable barrier. This allows the cell to operate safely while packing in significantly more energy. Sodium-ion cells take a different route. They swap out rare, expensive lithium for universally abundant salt, which drastically slashes the cost of production. The engineering trade-off here is physical volume. Sodium ions are larger, which decreases the total energy density of the cell. In exchange, manufacturers gain massive improvements in safety and scalability. Then there is LFP, lithium iron phosphate. Acting as a vital bridge chemistry, it removes expensive metals like cobalt entirely, trading raw power for a much longer cycle life and a lower price tag than traditional lithium-ion. All of these alternatives perform beautifully in laboratory tests, but inventing a better cell is practically meaningless if you cannot physically build millions of them. This is the scale barrier. Designing one perfect prototype is a laboratory success. Building the infrastructure to reliably and cheaply manufacture millions of them is a massive industrial hurdle. This chart illustrates the global lithium-ion market's projected growth. The industry has a massive head start. Looking at the steep curve from 2020 onward, current production volume makes it economically terrifying to rip out functioning factories to bet on unproven technology. Premium chemistries like solid-state are currently trapped behind this barrier because they require highly complex, entirely new manufacturing techniques to produce. Conversely, the true superpower of sodium-ion and LFP is that they easily drop right into existing lithium-ion factory infrastructure. In the energy sector, a battery's success is dictated by its manufacturability. A chemistry that is good enough and easy to mass produce will always beat a theoretically perfect design that cannot scale. We are now entering a great divergence. The monolithic battery is splitting into a specialized toolbox. Solid-state and advanced lithium-ion will become strictly high-end applications, reserved for premium electric vehicles and aviation, where long range justifies the high cost. Sodium-ion and LFP will dominate the mass market. For budget vehicles and everyday consumer electronics, dropping the price and increasing safety matters far more than extracting maximum range. For massive stationary grid storage systems, weight and physical size are entirely irrelevant. These installations will rely almost exclusively on cheap, bulky chemistries, like sodium-ion, to store renewable energy. Matching the exact right chemistry to its specific application enables economic and environmental efficiencies that a generalized battery could never reach. Traditional lithium-ion did exactly what it was engineered to do. It successfully dragged human technology into the rechargeable era. But we are now moving past a fragile monopoly of good enough and into a highly resilient, diversified chemical ecosystem. The next leap in human energy storage will not be a single miracle breakthrough. It will be the synchronized integration of a team of specialists. We are no longer looking for the perfect battery. We are simply picking the right tool for the right job.